Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 4, Integrals. Section 5.1, Areas and Riemann Sums.
Lesson 2, Definition of Area and Riemann Sums. Part 1.
So let's go to the next page where I have a bigger picture and it'll be a little bit easier to see those different subscripts. So I'll repeat that on the next page. What we're going to do now is break things up the way we talked about. I just blew up the picture a little bit. Here's my function again, y equal f of x. Here's my starting value of my interval a, my ending value is b, and here are those x values written a little bit more clearly because they're larger. So a is the same as x sub 0, and so when we get to the right hand endpoint of the first subscript, that'll be x1, and then x2, x3, and so on. The last ending point b is the same as x sub n, and the one right before it I was saying is x sub n minus 1. This is the ith strip, and its right hand endpoint is xi, so its left hand endpoint is x sub I minus 1. Well, let's see if we can figure out what r sub n would be. That would be adding up the areas of the rectangles, those purple rectangles, where we use the right hand side of each strip to figure out the height of the rectangle. And I actually drew in the picture for us so we wouldn't have to draw it. But r sub n, if you look at the very first strip right here, I've used the right hand endpoint to create the height of my rectangle. So my first approximating rectangle, excuse me, I kind of went over the line there, my first approximating rectangle is this high, and would look something like this. And what would the area of that rectangle be? Well, it's its height times its width. Its width is what we call delta x in general. In our particular example, we had a value for delta x, but now we're just going to call that delta x. So the width of this first rectangle is delta x. But how high is it? We're using the right hand side to figure out the height, the right hand endpoint. And so I'm going to be using this value x sub 1. And so it's going to be as high as this green vertical line under the curve at x1. And that would be f evaluated at x1. And now since f is a general curve and we don't know what specific equation it has, we have to just leave it as f of x sub 1. So this would be the height of my first rectangle, f of x sub 1, and delta x would be the width of that first rectangle. And so that would be the area of this first approximating rectangle. Well, let's go ahead and see if we can write down the areas of the others, and we do it exactly the way we did for our specific example. The next rectangle, I have to use the right hand endpoint on the second strip. So the right hand endpoint on the second strip would be x2, and I create a rectangle that is this high for this second strip, and so this is going to be what my second approximating rectangle looks like. And what is that height? Well, it's just f evaluated at x2. So my second rectangle is going to have height f of x2, and the width is still the same. All our widths are the same. We're calling that delta x. And we continue to do this all the way along. The very next one here, if I look at strip number 3, I would use the right hand endpoint there. I would create my little rectangle to be that high, and you can see that I've already done that for us. So that approximating rectangle looks something like this. How high is that? Well, it's just f evaluated at the right hand endpoint of that strip, which would be f of x3. So my next one would be f of x3 times delta x, and we keep doing this until we get to the end. And what would the last one look like? Well, here I am on the nth strip. I'm using the right-hand endpoint of that strip. That would actually be B, but we're also calling that x sub n. So that's what creates the height of this last approximating rectangle. So that rectangle is going to look something like this. And how high is that last rectangle? Well, it's f evaluated at the right-hand endpoint of that strip. So it's f of b, but we usually call that x sub n for these purposes. It's just a little bit better to use the same pattern that we used for all the sub-interval x values. So the very last one would be f evaluated at x sub n, which is really the same thing as b. And then I multiply by its width, which is delta x. We add all of those up, and now we have, in a very general form, how to find r sub n, the sum of the approximating rectangles when we create each rectangle using the right-hand endpoint on each strip. You notice in this case, for a function that is partly decreasing and partly increasing and then decreasing again, it's not always increasing or always decreasing on the interval from a to b, that some of my approximating rectangles are below the curve, and so they underestimate the true area under the curve, and some of my approximating rectangles hang over the top of the curve, and so they overestimate the area under the curve on that particular strip. So if your curve is partly going down and partly going up, when you figure out Rn, it won't necessarily be an overestimate as it was in our example. It was in our example because we had the square root function and it was increasing everywhere on the interval from 0 to 8. But if we have something that is decreasing, it would actually underestimate it, and if it's partly decreasing and partly increasing, then it's sort of a mixture of those two, which actually means that this will probably be more accurate, but we won't know that it's definitely bigger than the true area or definitely smaller than the true area. Okay, so that's our n. That's our estimate with n rectangles under a general curve y equal f of x on the interval from a to b. And now what I want you to do is to think about this question. What happens now as we let n go to infinity? And I drew some little pictures that are supposed to look like this function. I'm not sure they look exactly miniaturized version of that, but that's what I tried to draw down here. Here's my f of x, and here's the interval from a to b, and in this first picture I used two rectangles to approximate the area under the curve, and you know, it looks like it isn't too bad an approximation. In the second picture I used 4 rectangles, and it looks like it's getting to be a little bit more fine-tuned approximation. So this approximation will probably be better than when I only used 2 rectangles. And here I used 8 rectangles, and you can see that how much these rectangles are off by the little white area when it's below, or the amount that hangs over when it's above, is getting pretty small. So our error is getting quite small even at n equal 8 for this particular picture. And so we can see that that looks like it's definitely going to be a better approximation to the true area underneath the curve. And if I were to allow n to go to infinity, what would happen? Well, it would be just like the example with the root x function, excuse me, that we talked about earlier. And I should end up, as the number of rectangles gets larger and larger, with a better and better approximation. In the limit, if I allow n to go all the way to infinity and have an infinite number of rectangles that are infinitely skinny with widths that go to 0, I should get the exact area underneath the curve. So if we turn to the next page, notice what it says at the top, that this idea of going to an infinite number of rectangles to find the true area under the curve is actually going to become our definition of the area under the curve from A to B. So remember at the very beginning of this section, I mentioned that we don't even know how to explain to somebody else what we mean by the area underneath a curve. So if somebody says something like, "What is this green area? What are you talking about? Explain what you mean by area to me. I've never heard of that concept." We say vague stuff like, "Oh, it's how much space is in there," or something like that. And it's very hard to explain what we actually mean when we say the area, how much area there is. We tend to use the very word we're trying to define. So we said that we were going to start out just assuming one thing, which is that the area of a rectangle is the length times the width, or you could say the width times the height, which is what we've been using. So all we've done is to use that one idea that we're going to define the area of a rectangle to be height times width. And now what we've done is we've figured out a way to describe, based on rectangles, what the area under any curve y equal f of x is from a to b. So what I have in the green box here, I want to remind you, is not just a way of finding this area under the curve, it's actually a way of defining what we mean by the area under the curve in a very precise sort of way. So let's read the definition. It says, definition, the area A of the region S that lies under the graph of a continuous function f, so here's our continuous function f, that lies above or on the x-axis. In other words, f of x is greater than or equal to 0. That's another way to say it. On that interval from a to b. That's what we mentioned earlier, that it's continuous and is above or at worst on the x-axis, not below the x-axis on the interval from a to b. That area from a to b is, and here's capital A for this green area, the limit as n goes to infinity. So the limit is the number of rectangles becomes infinite of that sum that we just had on the last page. And what was the sum we had on the last page? We said it was f of x1 delta x plus f of x2 delta x plus, and so on, plus f of xn delta x. That, I'll just show it to you again for a moment, that was our Rn. So that was just adding up the areas of all the rectangles using the right-hand side of each strip to find the height of the rectangle. So that's what we had here for Rn. And we're just defining the exact area under the curve to be the limiting value of that sum as n, this number of rectangles, gets larger and larger and larger, and we're looking at the limit as n goes all the way to infinity. So another way to write this would be, we're defining the area as the limit as n goes to infinity of this right-hand estimate that we had, r sub n. So for any particular n, such as n equals 1,024 rectangles like we did in our last example, you'll get an approximation for the area under the curve. But if you allow n, the number of rectangles, to become infinite, an infinite number of infinitely skinny rectangles, then you get the exact area under the curve. And in fact, that becomes our definition of the area underneath a curve. Now, if somebody doesn't know mathematics, it still might be hard to explain to them what you mean by the area under the curve, but if they know some mathematics, you now have a way of explaining precisely what you mean by, oh, it's the amount of stuff that's underneath this curve, or it's the amount of area or space that's underneath the curve. It's not very exact, but this is very exact. Okay, a couple of remarks. So one remark is this, that this Rn that we found before we actually find the limit as n goes to infinity, the Rn that we had here for a finite number of rectangles, this thing, is actually a particular type of a more general kind of sum, a more general way of estimating the area under a curve that is called a Riemann sum. So this is one particular example of what's referred to as a Riemann sum. Riemann was a mathematician who explored this area of mathematics. So this is one type of Riemann sum, and we will look at other types. L sub n, which we'll talk about in a moment, where you're using the left-hand endpoints, is another type of Riemann sum, but there's a more general form that we'll talk about, the most general form for a Riemann sum, and these are particular examples of those. So I just wanted to get that word in there, that what we've just the sum that we've just created, the sum of the areas of those approximating rectangles, is referred to as a Riemann sum. Okay, the other remark I wanted to make is that if f is a continuous function, and that's what we were assuming up here, that f was continuous on the interval from a up to b, if f is a continuous function, it turns out that this limit always exists. And as we very well know from back when we were studying limits and also when we were studying derivatives, the limit of some expression may exist or it may not exist. We had lots of limits that ended up DNE, does not exist. So that's kind of a powerful thing that we're not proving here at this point. But it does turn out that if your function is continuous from A to B, no breaks in it, and actually it turns out even if it's piecewise continuous and has breaks at a finite number of places between A and B, this limit always exists. So that's really nice. You have a continuous function. That means that if you have a way of devising how to find the limit of an infinite number of things added together, then it is a limit that absolutely will exist. And I just wrote down here again just to kind of emphasize this idea that this definition we just talked about is the definition of the area under a curve. I just kind of wrote that again here, that the area, this green area that I've drawn here, I tried to draw like an infinite number of rectangles that are infinitely skinny. I don't know if you can tell with my pen marks on the video, but this area is defined to be the limit as n goes to infinity of r sub n. So this limit is our definition of the area under the curve y equal f of x on the interval from A to B. It's the definition of what we mean by that green area. Okay, well, let's go ahead and go to the next page and think about our left-hand limits. Let's consider doing what we did with the y equals square root of x function, where instead of using the right-hand endpoints to figure out the height under the curve, we use the left-hand endpoints on each of our strips to figure out the area under the curve. The only difference is that, again, we are going to be using y equal f of x, some general unknown function. We're going to be doing the interval from A to B, and we're going to be splitting it into n rectangles. And you notice, for example, on the very first strip here, I look at the interval from A, which is the same as x0, so from x0 to x1, and when I figure out the height for that rectangle, I use the left-hand endpoint, which would be x sub 0, and so the height under the curve is this green height right here, and that's what I use to create my first rectangle. And so I have used the left-hand endpoint to create the height of the first rectangle, as opposed to the right-hand endpoint that we did a couple of pages back. Well, what I would like you to do is to try to write out L sub n just the way we did R sub n 2 pages back, and see if you can write out what that sum would be in terms of the function f of x and in terms of our subdivision x values, x0, x1, x2, and so on. So pause the video, give that a try, and if you get stuck, we'll go through it together when you restart. Okay, well, let's go ahead and try it together. I'm going to look at this first rectangle right here, and I need its height times its width. Well, the width of all of these is exactly the same width that we had before. So the width of each of these subintervals is still going to be equal to delta x, and that's true for all n subintervals. So we know that the width is going to be delta x, but I have to multiply by the height. So how do I figure out the height? Well, exactly the same way that we did before, except that now we're using the height at the left-hand endpoint instead of the right-hand endpoint. So this is now our height for the first rectangle. Well, what is that height? It's the height under the curve at x0, so it's really just the function f evaluated at x0. So my very first height right here would be f evaluated at x sub 0. And then I multiply that by my width. Okay, for the second rectangle, so let me shade it in the other direction. I want to look at the interval from x1 to x2. I'm supposed to use the left-hand endpoint to figure out the height of my rectangle. And so that would be this green height. You notice the rectangle has already been drawn for us, just so that you didn't have to draw quite so much. And so for my second rectangle, I want to figure out how high is that. And it would be f evaluated at the left-hand endpoint. The left-hand endpoint is x sub 1. So that is the height of my second rectangle. So I would do f of x sub 1 times its width, which is still delta x. And we just continue this process. If I did the third rectangle, it would be exactly the same idea. I'm looking at the interval from x2 to x3 now. I use the left-hand endpoint of that little subinterval to figure out my height. So I'm using this green height, and you notice that this rectangle that's been drawn for us is at the correct height. And how high is that? Again, if I want to know how high it is, I'm just saying, well, it's whatever the value of f is at that x value. So it's f of x sub 2. So my third rectangle would look like f of x 2 times its width, which is still delta x. And we continue this process. I put dots on the picture saying that there are really some rectangles that are perhaps missing there. And same thing with our sum, I'm putting dots in between. And now we're going to write down the very last rectangle. So that would be the nth rectangle. Now we have to be a little bit careful to be sure that we stop at the right point. So I'm going to go ahead and shade in this rectangle. And we're looking at the interval from x sub n minus 1 up to b, which is the same thing as x sub n. Remember, we're using the left-hand endpoint, so I'm going to be using x sub n minus 1 to create the height of my rectangle. So you notice that this green height here under the curve is the height of the rectangle that was already drawn for us. So we want to know, well, how high is that? So let's see, that's the height at x sub n minus 1. So that would be a height of f of x sub n minus 1. So for my very last rectangle, the height will be f evaluated at the left-hand endpoint. So that's not x sub n, but x sub n minus 1. And then again, I multiply by its little width, delta x. So I hope that made sense to you. In a sense, it looks just like r sub n, except that the x values that we choose to plug into the function f are all shifted to the left by 1 because we're using the left-hand endpoint of each subinterval instead of the right-hand endpoint. So for r sub n, the right-hand endpoints, we started with f of x1. The next rectangle had a height of f of x2 and so on all the way up to f of xn. But for the left-hand endpoints, we start at x sub 0, then we do f of x sub 1, f of x sub 2, and so on, and we stop one to the left at xn minus 1. So we had an f of xn minus 1 there. Okay, well, I have a question down here at the bottom, and let's think about this question. We've done this sum, and we can see that these rectangles do, if I added up the purple areas, they do create an approximation for the exact area under this curve from A up to B. But the question is, if I let the number of rectangles go to infinity in this general case of L sub n, in other words, if I found the limit as n goes to infinity of this sum that we just wrote out, f of x0 delta x, plus f of x1 delta x, and so on. I won't write that third term, plus f of x sub n minus 1 times delta x. If I could somehow find the limit as n goes to infinity of that sum and let these number of left-hand rectangles grow to become infinite in number, so an infinite number of rectangles that become infinitely skinny. The question is, will that still come out to the correct exact area under this curve, just the way it did for the right-hand rectangles? Well, I hope it makes sense that it doesn't really matter whether we use the left-hand heights or the right-hand heights under the curve on each subinterval. If we allow the number of rectangles to go to infinity, we will still eventually get the exact area under the curve. And we'll get the same value for a that we did in using the right-hand limit. So let me just mention that as long as our function f is continuous on this interval from a to b, it turns out that the area can be found by doing the limit of the right-hand rectangles as n goes to infinity, as the number of rectangles go to infinity, or we can do the limit as n goes to infinity of the left-hand rectangles. These limits will always exist as long as f is continuous, and they will be equal to each other, and they will equal the exact area, or what we are defining to be the exact area under the curve. So when we did that definition on the previous page, let me just go back to that for a moment. That was this page. And we made the definition of our area of the region S, the area under the curve y equal f of x from a to b, and we said that that is going to be defined to be the limit as n goes to infinity of r sub n. We could have just as well made it a is equal to the limit as n goes to infinity of L sub n. These numbers that you get when you find the limit will be exactly the same as long as you have a curve that is continuous on the interval from a to b. So we could have defined the area that way just as easily. Okay, so let's go ahead and look at the next page. What I want you to do now is to try to expand your idea of what kind of rectangles we can use to find the area underneath the curve. We said we could use the right-hand endpoint of each subinterval to create the height of those rectangles, or we could use the left-hand endpoint of each subinterval to create the height of those rectangles. But I want to ask you this question. What if we didn't use the right hand or the left hand endpoints on each strip, each subinterval, but instead evaluated the height at some arbitrary x within each subinterval? So let me explain what I mean by that. Let's look first at this first subinterval here. I'm going to call that subinterval 1. Well, for the right hand rectangles, we used the right-hand endpoint. We used x1, and that's what we used to create the height of our rectangle. When we used the left-hand rectangles, we used the left-hand endpoint of this particular subinterval. So we used x0, and we found the height under the curve at that left-hand endpoint, and got, in this case, a rectangle that would hang over the curve. Well, what I'm suggesting is that instead we just go ahead and choose any x value between x0 and x1. It could even be x0 or x1, but not necessarily. So I'm just going to choose an arbitrary x value in between x0 and x1, and I call that x1 star. It's my arbitrary x value on the first strip. And what I do is I say, well, what would the height under the curve be at that x value? And you can see the height would be this red height that I've drawn in here. And when I create my rectangle, I make it have this height. So it has this width. It goes from x0 to x1, but it has a height that corresponds to the height under the curve at this intermediate value, this arbitrary value that I choose somewhere between x0 and x1. So my rectangle now would actually look like this. I won't shade it in too much so that we can see that red line, but my rectangle would look like this now. And at least for this curve and the way I've drawn it, it's a rectangle that has a height that's kind of intermediate between the left-hand height and the right-hand height. But it's some rectangle, and I think you can see that it still approximates the area under the curve on that little strip. Well, we do this in each rectangle. So now I'm going to go to the second strip, and I'm just going to choose some x value between x1 and x2. It could be x1, x2, or any number in between, an arbitrary x value, and I'm going to call it x2 star. And I just chose this value at random, but you could choose any one that you want to. And this dotted red line is going to be the height of this second rectangle. It's just the height under the curve at this arbitrary x value, x2 star. So I'm going to create a second rectangle. It will have a height that looks something like this. It's that red height under the curve. And here is my second rectangle. And we keep doing this until we get to the nth rectangle down here. So let's do it for the nth rectangle. I choose any value that I want to between x sub n minus 1 and x sub n. So it could be x sub n minus 1, it could be x sub n, or it could be any value in between. So I'm just going to arbitrarily choose this value, and I will call it x sub n star. It's my arbitrary x value within the nth strip. And again, I say, well, what would the height under the curve be at that x value? It would be the height of this red dotted line. And I'm going to use that height to create a rectangle that stretches widthwise from the left side to the right side of my strip. And so my last rectangle would look something like this. And would again be some rectangle that perhaps is intermediate in between the rectangle that you'd get if you use the left-hand endpoint or the right-hand endpoint. I guess that would be true in this case because the curve happens to be always decreasing on that particular interval. Okay, well, let's see if we can go ahead and write out what the sum of the areas of these purple rectangles would be using these intermediate x values for the height of the rectangle on each strip. Well, if I look at my very first rectangle here, it's still going to have a width of delta x. All of the widths are still equal to delta x, where delta x, remember, is the width of the entire interval from A to B divided by however many rectangles I am splitting it up to, n rectangles. So all of these still have a width of delta x. Okay, that's great. So when I look at my very first rectangle and I think, well, I need its height times its width, I know that the width of that rectangle is delta x. Now, what's the height of this first rectangle? Well, the height is this red dotted height that I have here. And what is that? It's f evaluated at this x value, x1 star, that intermediate x value that I chose. So that is the height of my first rectangle. So my height here for my first rectangle would be f evaluated at x1 star, and then times delta x, its width. And same idea for the second rectangle. We know its width is delta x. We want to know, well, how high is the second rectangle? Well, that's just going to be f evaluated at, it's as high as this red dotted line here, and that would be the function evaluated at my second arbitrary x value, x2 star. So my second rectangle would have a height of f of x2 star multiplied by its width, delta x. And we keep going all the way to the nth rectangle. I'll put some dots in there to indicate the terms that are missing. And for the nth rectangle, the height is this red dotted height. That would be f evaluated at, well, this red dotted height goes along with x sub n star. So the height of that rectangle would be f of x sub n star times delta x. Well, the question becomes, when we use these intermediate heights, do we still get an approximation for the area under the curve? And I think you'll agree that you're still going to end up with some kind of approximation for that area. In fact, it might be, depending on the function, a little bit better approximation than either using always the left-hand endpoints for your heights or always the right-hand endpoints for your heights. And if you want to, you can draw in a bunch of rectangles that have heights that are evaluated at some intermediate value that you choose on each subinterval, and try to convince yourself that the sum of all of these areas will be an approximation for the area under the curve from A to B. Well, now what I want you to do is think about, again, letting our number of rectangles go towards infinity. So if we thought about the following, if I did the limit as n goes to infinity of this sum, f of x 1 star delta x plus, I'm not going to write that second term, all the way up to f of x n star delta x, what would happen? So I'm going to subdivide into more and more rectangles. On each little strip, I'm still going to be choosing some intermediate x value, some arbitrary x1 star, x2 star, and so on. So each of these, for every number of rectangles that I choose, is going to be some kind of an approximation for the true area under the curve. As n goes to infinity and the rectangles become more and more numerous, and each rectangle becomes skinnier and skinnier, the widths shrink towards 0, will this still eventually give me the area under the curve? So when I find the limit as n goes to infinity, the question is, will I get the exact area under the curve? And the answer is yes. Again, as long as f is continuous on the interval from A to B, you'll get that same area that we define to be the limit as n goes to infinity of the Rn, where you always choose the right-hand side. So this limit will exist, and it will equal exactly the same value as the limit as n goes to infinity of Rn, and exactly the same value as the limit as n goes to infinity of the Ln. I think I mentioned before that the Rn, I guess I should actually put this arrow here. Let me remove that, but this arrow right here, this sum that we found is actually another special case, an example, or another special case of a slightly more general form for the sum of these kinds of rectangles. So I'm going to say it's a special case of what's called a Riemann sum. And that's actually what we're going to talk about next, is, well, what's the most general form of this Riemann sum that I've been alluding to? So the Rn, the Ln, and also this sum that we talked about where we're using the intermediate heights are all examples of a more general form for general way of creating an approximation with rectangles under a curve that is called a Riemann sum. Before we go to talking about the Riemann sum, though, let's return to our example.